In this class, we're going to look at dithering. Dithering improves the quality of images that have a limited palette. We've already seen how an image with 16 million colors can be reduced to 256 by using a lookup table. With only 256 possible values, each pixel then requires only 8 bits instead of 24, and this is a big saving. However, the new color palette could be quite limited, and this might be very noticeable. Take a look here at this 24-bit image. Now, it's easy enough to see how with this limited range of colors that this could probably be coded using 256 colors without much difficulty. But what about 5 colors? Here you can see that some of the pixels have been matched perfectly to one of the 5 colors in the palette, but others haven't. There are many more subtle shades of orange in this image than can be accounted for in 5 colors. And so they're just assigned to the closest match from the 5. That gives this banding effect here. Now let's take a look at this image here. This too has only 5 colors, but it looks a whole lot better. The smooth gradient from orange to yellow here has been preserved using dithering. Dithering simulates a desired color that's not in the palette by positioning pixels of available colors in such a way that from a distance they have the appearance of the desired color. If we take a closer look here, you can see that there are still only 5 different colors of pixel. The intermediate shades are simulated by mixing darker and lighter pixels. The right colors in the right ratios can create the illusion of the desired color. So we can simulate the missing colors from the palette with the colors that we have available. To create the illusion of a simulated color, the average RGB values of the pixels must be close to the RGB values of the simulated color. Take a look at these 2 shades of grey here in a chessboard pattern. The darker grey has RGB values of red 50, green 50 and blue 50, and the lighter grey is 150, 150, 150. Because the light and dark pixels occur in equal proportions, the average darkness of this area when viewed from a distance is the average of the pixel values. So it's red 100, green 100, blue 100. Here, grey pixels with RGB values of 100, 100, 100 are mixed with blue pixels with RGB values of 0, 0, 200. The average redness of these pixels will be 50. The average greenness will be 50, and the average blueness will be 150. So from a distance, these pixels will have the appearance of a color that is red 50, green 50, blue 150. When the pixels don't occur in a 50-50 ratio, calculating the overall average is a bit more complicated because it has to be weighted according to the ratio. Here the blue pixels have an RGB value of 25, 10, 100, and the brown pixels are 125, 50, 0. However, the blue pixels are 3 times as common in this dithering pattern than the brown pixels. So the calculation of the simulated color will include the RGB values for the blue pixels 3 times. It's a weighted average. The simulated color here has an RGB value of 50, 20, 75. Image editing applications like Photoshop can dither an image using any palette of colors you want. However, dithering should only be used at the end of the editing process, if at all. Once images have been dithered, it can be very difficult to edit them any further. They generally don't give very satisfactory results. So dithering simulates a missing color from the palette. It's a color that we want, but it's not there. However, we can simulate the appearance of that color by mixing the colors that we have in the palette in the appropriate proportions. Now, at its simplest, you could have two colors in a 50-50 pattern, but you could have several different colored pixels mixed in unusual ratios to give you pretty much any color that you'd like. So dithering can fake a color that we're looking for using whatever colors we have available.